Hi, my name is Nikolas Schonsheck. I study homotopy theory at Ohio State with John Harper. I'm finishing up my PhD next year and am on the academic job market. So my research focuses on problems dealing with completion, localization, and functor calculus in the context of operatic algebras and spectra. One of the neat things about this setting is that there are a number of very strong analogies with the more classical setting of spaces, and I'll try to highlight those throughout this video. So one direction of my research begins with the observation that although homotopy groups are the main invariant of both spaces and O-algebras, they're also very difficult to compute. And because of that, it's often beneficial to look instead at their homology groups, which are a coarser invariant that throws away more information, but does so at the benefit of being more computable. Now, there are a number of deep theorems in the classical setting of spaces which relate homotopy to homology via localization and completion, for instance, those of Bousfield and Bousfield-Kahn. One goal of my research program is to establish similar relationships in the setting of O-algebras, where topological Quillen, or TQ-homology, plays a role analogous to integer coefficient singular homology in spaces. So a useful comparison to keep in mind here is that spaces and singular homology are analogous to O-algebras and TQ homology, which is actually weakly equivalent to stabilization. I'm particularly interested in completion with respect to TQ homology. Now, given a space or O-algebra X, the idea of homology completion is that we want to build sort of the part of X that homology sees. And there are cases when X is actually weakly equivalent to its completion. And what this is telling us is that that space, or O-algebra, can be recovered actually up to weak equivalence with purely homological information. And in studying TQ completion, I've proven the following theorem. So this says that TQ completion preserves fibration sequences in which the total and base O-algebra are zero connected. So that is to say, if we take such a fibration sequence and hit it with TQ completion, it's still a fibration sequence up to homotopy. Now, it's known from a result of Ching and Harper that under the assumptions of this theorem, E and B are TQ complete, and my strategy of proof is to show that in this case, F is as well. And consequently, this theorem also establishes a new class of TQ complete O-algebras, namely homotopy fibers between maps of zero-connected O-algebras. And a similar statement also holds if we replace fibration sequence with homotopy pullback. The second major avenue I've pursued in my research deals with functor calculus, and I'm particularly interested in the question, what can functor calculus tell us about completion and localization, and vice versa? Now, the basic beautiful idea of functor calculus is that just as we can approximate a large class of functions from, say, R to R, we can approximate sufficiently nice homotopy functors by simpler ones, which we think of as nth degree Taylor approximations. In contrast, though, to the identity function and its Taylor series in classical calculus, when we work in an unstable setting, like spaces or O-algebras, the Taylor tower of the identity functor actually contains a great deal of interesting information and structure. Now, Goodwilli's Heyer-Blakers-Massey theorem tells us that the Taylor tower of the identity converges strongly on all one-connected spaces. And the analogous result in O-algebras, due to Kuhn and Harper-Hess, is that the Taylor tower of the identity converges strongly on all zero-connected O-algebras. I'm interested in the question, what happens in the absence of these connectivity assumptions? So, for instance, outside of the radius of convergence. In the case of spaces, Aron and Kankan-Rinta showed that for any connected space, the Taylor tower of the identity converges to the completion of that space with respect to stabilization. And I would like to explore the analogous question in O-algebras, where it's known that stabilization is weakly equivalent to TQ, and hence they're both weakly equivalent to P1 of the identity. So this is the subject of ongoing work, but I have proven the following preliminary result in this direction, which says that if we have an O-algebra A, which is only -1 connected, but the TQ of A is 0 connected, then the Taylor tower of the identity, so P infinity of the identity here, recovers the TQ completion of A. The basic idea of the proof, which is motivated by Ron Kankanrinta, is that, well, we want to say something about the Taylor tower of the identity, but it's actually easier to analyze the Taylor tower of iterates of stabilization, or TQ. So we resolve the identity functor with respect to TQ and analyze the resulting cosimplicial tower. And by taking Holem in two different directions, we get a zigzag of weak equivalence between P infinity of the identity and TQ completion. I'm also able to show that without any connectivity assumptions, P infinity of the identity can always be recovered from its TQ completion, from its TQ homology, via a long TQ completion tower. So I'd like to tell you now about a number of questions related to the work I've just shown you that I hope to pursue in the future. So the first is to establish a fibration theorem, sort of akin to this first result, but for P infinity of the identity rather than TQ completion. The strategy I use for TQ completion doesn't seem to easily carry over to this situation, and since it's unknown precisely when P infinity of the identity and TQ completion agree, the conditions may very well be different. The second stems from the observation that since TQ is weakly equivalent to P1 of the identity, completion with respect to TQ homology is the same as completion with respect to P1 of the identity. And when we think about it in this way, it suggests that we can maybe start playing with the parameters 1 and identity. So I'm interested in studying completion and localization with respect to Pn of f, both in spaces and O-algebras. The third deals with the long completion tower mentioned in Theorem 2. And the idea, inspired by work of Dror and Dwyer, is that just as we iterate the Hurewicz map to build TQ completion, we can iterate the resulting map, x to its completion, to build another resolution and continue inductively. So I'm interested in incorporating this kind of technology when thinking about, for example, completion with respect to Pn of f. In addition to these questions, I'm also hoping to diversify my research program as I enter the next phase of my career, and am particularly interested in the chromatic point of view and how it interacts with Goodwilly's functor calculus. So for example, Kuhn has shown a striking relationship between functor calculus and Morava K-theory, and in particular that the Taylor tower of a homotopy functor from spectra to spectra splits after Kn localization. So more succinctly, functor calculus plays nicely with Kn localization. I'm curious if similar results can be obtained for Kn completion. I'm also interested in a number of problems in graph theory, which are accessible to undergraduate students. The first of these, namely the game of cops and robbers on graphs, stems from my own work as an undergraduate. The second deals with graph coloring, which was the subject of an RU at Ohio State I volunteered to help mentor this past summer. And I'd be more than happy to discuss the specific problems I have in mind at our virtual meeting. So to keep this video appropriately brief, I think I should wrap up, but I hope you'll stop by my virtual booth and ask any questions you might have. So I look forward to seeing you soon.